He's going to talk about data fetching and list Next.js, React, query, and their BFF.
Thank you very much. So we're going to continue the theme of architecture in front-end, and that's going to be the afternoon pretty much. Can everyone hear me? Yes? No? This is not turned on. Hello? Okay, cool. So we are going to be talking about data fetching unleashed, solving the problem of resilient and performant data fetching in an unideal world. So we're going to be talking about Next.js, React Query, and the BFF pattern. So that doesn't necessarily just stand for best friends forever. So a little bit about myself. As I said, I'm an engineering manager at Navro and also the front-end subject matter expert, helping with the technical strategy over there for designing a API and portal for financial solutions and being able to do global payments and collections. I'm also from Switzerland, the land of cheese, chocolates, and watches, and also from Pakistan. My passions are web performance and engineering leadership, and I'm also a frequent open source contributor, particularly to a project called Raycast. You should definitely check it out. So the first thing I want to do is set the stage. There is no one-size-fits-all solution. The favorite answer to any question for a programmer is it depends. So this pattern, these architectural things that I'm going to be showing you in just a minute, that's not just going to be for every single project. So we can't just copy and paste it all across the board, but this is going to work for a particular type of situation. It's mainly going to be a story about a problem I tried to solve around about a year ago, and that solution is still holding and scaling till today. This is also not a tutorial. We're not going to be building an app from scratch, but we've got 3 demos, a little bit of code, and some architectural flow diagrams to look through. And I've got just about 20 minutes to do that before Lena kicks me off. So we won't cover everything. There are lots of libraries, a lot of different patterns that we're going to do. This is just a starting point, so we're going to just touch the surface. It's going to be the tip of the iceberg. And then finally, I want to just put a little bit of a note around pragmatism and around premature optimization. You can have all the amazing patterns, all the resilience patterns in your application. You can make the most performant components, use the best state management libraries, but if you've only got one user, there's not much point in doing that. So you have to build something that's valid for the state of your application, the growth of your application, the scaling that your application is going to go through over time. So it's good to understand all these concepts. It's not good to put all these concepts from the get-go in your applications. So think about if you're pre-optimizing or you're doing it at the right time, and it's a data-driven approach. So what's the problem statement? What are we trying to solve today? What challenges do developers face in creating a seamless user experience due to complex data fetching and management? Something I would think almost everyone has been solving for since they've started programming. Moving forward, why bother do this? Why is it interesting? Milliseconds are crucial for user satisfaction in the digital space. Quick loading times are directly related to user happiness. Pages that load in 0 to 2 seconds, which is also known as the golden window, have the highest conversion rates. And there's also some research that shows a 32% increase in likelihood at bounce rates when page loads increase from 1 to 3 seconds. Moving forward, what are the technologies that we're going to be looking at today? If React is the library, then Next.js is the framework, and that's what we're going to be using today. Next.js has got a lot of cool features. I'm sure you can read those up in your own time, but a quick highlight of those are going to be server-side rendering, static-side generation, file-based routing, and API routes. Then we're also going to be marrying that with React Query, which is a powerful asynchronous state management library. React Query actually is often confused with a data fetching library. React Query, in fact, actually is a state management library that helps you manage global state. It just so happens to be really good at helping you fetch that data to and manage it and cache it. So what does React Query give us? Automatic caching and background updates. You can fetch, cache data, update it for all your React components. Optimistic updates. So when you want to send off a request but already change the UI before the response comes back, React Query is really good at integrating that. Pagination and infinite loading. When you've got a lot of data to show, you don't want to show a list of 1,000 things. You may paginate those. That's going to optimize your pages. And then prefetching data before it's needed on the server or via various methods. React Query really helps with that too, to make sure you've got a snappy user experience. And finally, cache invalidation is a notoriously difficult problem, and React Query helps with built-in cache invalidation. So Bare bones data fetching. The problem that we're trying to solve, the problem that I tried to solve around a year ago is our front-end team needs to design a dashboard chart that displays the distribution of birthdays for the top 5,000 users in our system. This is just a variation of the problem. We weren't actually looking at people's birthdays, but this was actually for payments and transactions. The data source is available via an API, which returns a list of users with all their data. The limitation, the backend team is unable to provide a new endpoint or a data warehouse that returns the required data format, and there's a limit of 1,000 users that I can fetch on each request. Now, in software development, we talk a lot about sometimes ideal scenarios when we have everything ready for us, all the resources possible, but that's not how the real world works. If you've been in any software team, there are always delays, there are capacity issues, there are just things that you need to be empowered as a front-end developer to solve without relying on external teams. This is especially if, for example, your in-house built API is an external product and you're selling that as an external product and you can't necessarily add new endpoints to suit your front end because that's going to have to go through breaking changes, potentially deprecation policies, and so on and so forth. So you've got to start getting creative. How do you make an optimal solution in an unideal situation? So demo one, we're going to start looking at an architectural model. Then we're going to look at the demo app. And then we'll see what we're implementing from the start and how we're going to evolve that over the next couple of demos to an ideal solution. So this is what our application looks like. It's just a simple chart. It's got a distribution of how many people's birthdays are there per month. And we've got 5,000 individuals to count for. In our basic version of our application, how are we designing this? We've got a UI. Because there's a limit of 1,000 users of data that I can request for in every single API call, I've got to make 5 API calls for that 5,000 pieces of data that I need. Then, with a good user experience comes a loading state. Something's happening in the background. We're fetching information. We've got 5 promises that need to be resolved. We have a potential happy path. So if everything's all good, we'll take the data, we'll map it to the structure we need to send to our props. Then we'll set it in state. We'll render the UI. However, there's a problem there. Depending on the state management solution you have a risk that every time you make a state change, your component's going to re-render, it's going to re-trigger the fetch. And if you're re-triggering a fetch of 5 parallel requests multiple times, you risk a 429 response from that API because you're overloading it, you're stressing it. Especially if you're paying per request, that costs money, and especially if you have an API with rate limiting. So if there's a sad path, it doesn't respond for some reason, we do what any normal system might do is you keep persisting the loading state. You're going to keep on showing it. Nothing's resolved so far. And you're going to attempt to retry. It didn't work time 1, so I'm going to do it all over again. And that whole path starts. So let's say we're doing this with custom logic. The problem with that is it needs testing. It needs maintenance. It's subject to bugs. There's state management complexities. If I don't handle my state management correctly and I re-render components at the wrong time, the refetches trigger, start overloading and stressing my server. The data mapping effort is on the client side. So there's potential needs for memoization and optimization there. There's a lot of effort in calculating, manipulating data. And there's no optimization at the payload level. Remember, we're using an endpoint that isn't necessarily designed for our front end, so it may have redundant data in it. So if we look at the demo, I'm going to refresh this page, and you're going to see 5 requests triggered. This is painfully slow to look at. And it's going to be returning a lot of information right now. If we see every single request is returning around 475 kilobytes, making around the total payload size of 2.3 megabytes. If we were using local storage as a cache solution, that would not be viable because after 2 bulk requests like this, you've almost run out of local storage usage in most browsers because it's around 4 to 10 megabytes depending on the browser you use. Then if I try to hide this UI and show it again, that state change, because it's not optimally handled, is going to re-trigger all the fetch requests. And now I have, again, data that is not necessarily stale. I don't want to refetch it, but because I've designed my state management poorly, that's just happening as a side effect. So if I dive into the code a little bit, this is a custom solution. What we're doing is we have a use fetch data function. It uses a fetch under the hood. It's going to go query an API. It's going to go get fake data, which is making 5 parallel requests under the hood. Then we're going to do some effort to map that data. The data isn't necessarily in the structure we wanted, so we're going to get the birthdays by month. We're going to map the chart data, then we're going to set it in state. And the story starts all over again the second you hide it and show it again. Because again, this component that's rendering the chart is a child of the parent that controls the state. So again, you'd have to rethink your state management for this to work really well. So one more thing just to show, if I look at the data over here, every single object that's being returned has address, bio, city, company, country, things that I do not need for my front end. So I'm getting a much larger payload than is needed to display all the information that I need. So this is not an optimal solution. This is also going to add memory usage. This is also going to strain your cache a little bit more. So what do? Moving on to their best friend forever, which is the BFF pattern, otherwise known as a transformation bridge or an aggregation proxy. So this is a pattern that you can use and adapt essentially a backend that you don't have much control over for your front end's usage. So you're adapting for your platform's requirements, whether your front end's a mobile, whether your front end is a web application, whatever it may be, you can cater for the unique data requirements and formats that needs. You're decoupling concerns here. So if you have got a large team and you want to dedicate 1 or 2 individuals to work on that proxy, on that aggregation layer, they can do that and they can work on optimizing that while the rest of the team is working on the UI layer on the front end. Then you can also optimize performance there. If I take that large payload that I'm receiving, around 2.3 megabytes, and I map that on the server, and I really reduce that to the bare minimum, I'm sending only what my front end needs, which means if my backend server has a great network bandwidth, it can go fetch that information real fast. And if my mobile phone or any other device is strained on the front end, I only need to receive the minimum amount of data to make that work. So you're also optimizing on the network level for this. And you can have a streamlined API evolution. You're not messing between the front end code and the back end code. You've got a clean separation of concerns. Any errors that occur on that API handler, that proxy you create, it's going to encapsulate those. You can observe those with tools like Sentry, so on and so forth. And you're kind of saving yourself from a little bit of pain of error handling that on the front end. So what could the payload optimization look like? This is the object we're receiving, 5,000 of these. We don't need that information. Moving forward, we're going to restrict that to this amount of information. Now we're going to look and see what's changed in the architectural diagram. So model 2. If I move over here, we're starting the story all over again at the UI. We're going to make now 1 API request to a Next.js API handler. You can build those in with Next.js. That's really cool, one of the features that it has. If you're using a React application, you can just spin up a Node.js microservice. It's not something that's tied to Next.js. This is a pattern that can be used with any type of framework. That API handler is going to make 5 parallel requests. The same thing we're doing on the client side, it's going to move that effort to the server side. Happy path. We have that server data returned on the server. We're going to map it there. The exact same thing we're doing on the front end, we're doing it now on the back end. We're going to send that data to the client, set it in React state, render the UI. However, we're still subject to the same state problem, which is if I don't handle my state correctly, I click some change, it's going to start that fetch over again. We're still straining our resource. So what are the benefits we have here? The payload can be optimized. Data is pre-mapped and sent. We've got a clear separation of concerns and a single request failure rather than having to handle multiple request failures. So let's look at a little bit of a demo and see how our front end has started to improve with this. So I only have to make 1 request. Isn't that a little bit faster now? That was a lot faster than the previous one. Can we see how the size of that payload? 666 bytes versus 2.3 megabytes. I'm not sure if my math is right, but I think that's a little bit smaller than what we saw before. Now, if I have a look at what is being returned, just the data that I need for my chart. How many birthdays, what the month is, and that's exactly what I'm going to inject right into my props. However, we're subject to the same issue where if I hide and show that, we're going to start that loading process all over again and fetching the data. It's still fast, but we can do this better. So I think I'm moving straight to demo 3. So if we look at that architectural diagram, we're going to start again at the UI. And now we're using React Query. So we're not going to have any custom data fetching solution. We're going to use React Query out of the box. Now React Query tracks and controls the loading state by itself, not something that we have to do, not something that we have to maintain. Our server is still going to be making those 5 API requests. If it's happy, the data is mapped, same as before. The data is now sent to the client and cached on the client. You can now choose if you want that to be in-memory cached, or you can have it as an offline cache. It depends on the use case. Now React Query will derive the response it received. You don't have to do that yourself. It'll render the UI. And now if there's a React state change, we're going to check the cache first. If there's a cache hit, we're going to go straight back to rendering the UI. We're optimized already. If there's a cache miss, we're going to start that process all over again. And we are going to start with a loading state, 5 API requests, so on and so forth, moving forward. So what's changed here? The library controls the loading and error states. Optimized payload can be cached, and you can use multiple caching strategies for that, depending on your application. You're deriving the state directly from the response. Stale data management is there too. You decide when your data is stale. Either it's stale after 60 seconds, or it could be after 60 minutes. You decide. React Query handles that. Your state management is managed for you. You don't need to use any local state. You don't need to fetch the data, put it in a use state. React Query will handle that, and you can actually use React Query, depending on the query keys, and I'll show that in a second, in any of your children or sibling components, and it will derive the response and the state from that same cache. So it's not going to refresh the data. You don't have to pass it around. You don't have to put it in a global state store. We're going to limit refreshes with re-renders, and we can configure the resiliency. So if automatic retries don't work, and retries are really a pain to implement, what you can do is you can add delays. Retry 1 happens. I don't do it immediately. I wait 100 milliseconds. Retry 2 happens. I wait 500 milliseconds, whatever it is. Then you can also implement an exponential backoff strategy, which means that if your API, you don't want to hit it every single time with the same delay interval, you can have an exponentially increasing interval. So the first retry is in 1,000 milliseconds, second one in 2,000, then 3,000. And APIs with rate limits or timeouts or something like that, it's going to be a lot easier to recover from those states. So you can use different strategies, and those are built in. And we can do one more thing. So if we move over to model 4, we're actually not starting at the server. Or actually, before this, I'm going to show the React Query code. So if I look over here, now React Query is handling all the data fetching for us. We can check if it's still currently fetching, so it handles the loading state. We have the stale time, and we have query keys, which means that I'm telling React Query that faker and whatever quantity I'm fetching for, depending on the query parameters, is what I want to store as the key for this information. And every time I reuse this hook somewhere else, that's where it's going to derive the state from. That's how it works as a global state management. So the last thing is we're going to look at the server. So this time, to optimize it even more, we can actually balance the load and move it over to the server and pre-fetch the data. So in an ideal world, we'll make the query on the server, and the code looks like this. And you'll have get server-side props right at the bottom. And what get server-side props is going to do is it's going to create a prefetch. It's going to use the same query key. It's going to fetch the exact same data, and it's going to create a dehydrated state, send that to the client. It's going to hydrate the client on the client side, and then React Query will derive the state from there, and it won't have to fetch. But this is subject to one problem. That problem being that what if my request takes 3 seconds to resolve? The user's not going to see anything. That's also problematic. So another resilient strategy that you can implement is timeouts. So if you see over here, I've put 1,500 milliseconds. And I'm telling this function that if my server-side response does not resolve in 1.5 seconds, abandon it on the server, go direct to showing the UI, show some loading state so there's interactivity on the website, and try to recover yourself on the client side. And this way, we're making our system more resilient by setting a timeout. And so you're doing the exact same thing as before. You're optimizing the payload. You're attempting to retries the way you did. You're trying to prefetch and optimize for a better user experience on the server side. But if that doesn't work in an ideal scenario and it's still taking too long to resolve, you're doing it all on the client side again to recover from that state. So you're trying to get the best of both worlds when your network connection is optimal. And if we look at the final demo, we'll actually see that if this works really well, right now it didn't resolve fast enough because the network connection is slow. But if I increase this to 2,500, and I believe I'm running a build server, Bear with me. Then I'd put 25,000. Wouldn't make a difference in this scenario. Either way, I'm trying to have a timeout that is larger than how long it will take the request to resolve. If I load this, and it takes a little bit of time for that server to kick up, you should see that it's going to show immediately, and we're going to have no loading state. So it might take a second for that to pop up. OK, cool. So I'm going to just retry that one more time. Let the demo gods be with us. Cool, that was instant. So now it's